Thanks everyone for coming. This is NET401. My name is Mike Furr. I'm an engineer with AWS in the EC2 organization. And today we're going to be talking about network performance. So as a quick overview of what I'm going to be talking about today and what you can expect from this session is we're going to do a little bit of a deep dive into TCP. So TCP runs a lot of our applications. And so we're going to go through, and since this is a 400-level talk, we're going to go pretty deep into the details of what makes TCP go. Of course, I'll give a little bit of a refresher just to kind of get your minds refreshed about some of these concepts, but expect some details. After I talk about TCP for a bit, we're next going to talk about some tooling. So TCP can be a pretty complicated protocol, and so it helps to have the right tools to be able to inspect and figure out what's going on within TCP itself. After we talk about some ways to kind of inspect things and make changes to your TCP stack, we're going to then look at some applications. So these applications I put together just for this talk, they're toys, they're examples, and I'm hoping what you take away from this talk is not that I get a particular change in behavior in these applications, but rather that you get a new set of tools in your toolbox so that you can go and explore and experiment and change with your particular applications and hopefully improve the performance of them. Network performance is notoriously difficult to get right, and so any kind of general statements tend not to be helpful, which is why I want to give you the tools to make the decisions yourself about how to improve the performance of your particular application. So I've been with Amazon for about 8 years now, a little over that, and I really love working on the cloud. And during that pretty much entire period, I've worked on EC2 and EC2 networking, VPC, and things like this. And during that time, I've really kind of come to love TCP. TCP is just a fascinating algorithm, and it just runs so much of the internet. And of course, everyone knows TCP is a transmission control protocol, and it runs on everything from if you're checking your mail on your phone to if you're calling a web service API on your desktop. And I think one of the reasons that TCP is so popular is the abstractions it gives you. So the two kind of most important features that I think drive this are, one is that you don't have to worry about the specific of networks. So a lot of our networks are based out of packets. But TCP's model is a streaming model. So as an application, if I want to have a TCP connection, I open up a connection, and then I start sending bytes. And I usually send bytes by writing them into a socket. I don't have to care about how big of a write to do in terms of how the bytes are going to be split up on the network. I just write some bytes, and I know that they'll be delivered to the other side. And it's TCP's job, not mine, to make sure that, for one, all the packets do eventually get there, that none of them are dropped, that none of them are reordered, and that that the performance of the stream is as high as it can be. So one of the things that TCP does as well is flow control. It makes sure it sends as many packets as it can without overwhelming the receiver. So let's talk a little bit at a high level how TCP works. If I was walking down the Vegas Strip and I was talking to a random person on the street, and I said, what do you know about TCP? I bet you they'd say three-way handshake. I bet you the first things out of their mouth would be SYN and ACK. So of course, the three-way handshake, what that means is that when you do that, you're establishing a connection. So a connection in TCP is a bidirectional connection between the sender and the receiver. And in fact, it's full duplex, right? The sender and receiver can send at the exact same time. And again, this is an abstraction. It's helpful for application programmers to think about TCP as this nice bidirectional pipe that we can just shove bytes into, and they'll pop out the other side. As we start to dig into the details of what actually makes TCP go, however, it's helpful to break this down and not as one bidirectional pipe, but as two separate unidirectional pipes. And there's a couple of reasons for this. One is that the path that packets take to get from one side of the connection to the other might be different than on the reverse path. It might physically traverse different routers along the path, or even if it did traverse the same routers in both directions, the state of that router might be different for the ingress and the egress bytes. Think about if I have a streaming delivery service or streaming video service, it's going to have a very asymmetrical bandwidth utilization on those links. The second reason it's really helpful to think about TCP as a pair of unidirectional channels is that the real power of TCP, the place where it gets to make all of its decisions, is actually at the sender. If I'm a receiver, if someone sends me a packet, I don't have very much choice. I either have room for it, in which case I'm going to put it in a receive side buffer, or I'm going to throw it away. That's all I get to do. There's very limited choice. But as a sender, I have a lot of control about how fast, how many, and all kinds of different knobs and parameters about how to set up this, or how to best utilize this connection. And so we really want to talk about the sender on both sides to get the best performance out of any given TCP connection. Now, as we dig into the details of TCP, you might remember some of these academic terms: receive window, congestion window. These are the main knobs that kind of control how TCP works. And we're going to go into a little bit of the details of those today. So the receive window is something that, as its name suggests, is maintained by the receiver. And it's signaled back to the sender. And the purpose of the receive window is to tell the sender how much space I have in my receive buffer. So when you set up a TCP connection, your kernel is going to allocate a certain number of bytes in the kernel to accept packets, and it will queue them there. And every so often, your application will execute a read system call, reach down in the kernel, and read a chunk of those bytes out of the buffer. So if the buffer is full, if your application isn't reading those bytes out of the buffer, there's no point for the sender to send more data. If Jack is sending bytes to Jill and Jill's buffer full, she just says, no thanks, don't send me any more. There's no point in doing it. They're just going to be dropped on the floor. And so it's Jill's responsibility to tell Jack about the state of her receive buffer. Now, this has real consequences for the amount of bandwidth you can get in a connection. Now, a lot of you may have heard of the term bandwidth delay product. Bandwidth delay product is when you take the round trip time of a connection and you multiply it by the bandwidth you have on that connection. And what that tells you is how many bytes you can actually place on the wire at once. If I'm blasting full rate at the full bandwidth and I know my round trip time, I can now compute how many bytes I can actually have in flight without dropping any. Now, where the receive window comes into this is it imposes an artificial cap on the number of bytes we can have on the wire. So what I've done in this slide here is I've actually solved for a different term in that equation, in the bandwidth delay product. I say, if I know my receive window because it's capped, let's say it's 100 kilobytes, and I know my round trip time because, unfortunately, we haven't quite figured out how to change the speed of light. That's pretty much fixed. So if I have a 100 kilobyte receive window and a 2 millisecond round trip time, then my effective bandwidth, by the way of the bandwidth delay product equation, is 400 megabits. So 400 megabits is pretty good. You'll get a lot of transfer out of that, a lot of decent performance. It's not great, but it's pretty good. Now think about what happens if we take the same equation, but instead of 2 milliseconds round trip time, let's say it's 100 milliseconds. So 100 milliseconds isn't too high. It's about the time it takes to go across the United States and back. And if we use this equation there, we find we're only going to be able to max out at 8 megabits. Now, 8 megabits is not anything related to the size of the fiber connection between the routers along the network path. It doesn't matter how many waves are on there. It doesn't matter what kind of network card it has. This is purely being influenced by the artificial restriction that the receive window places on the connection. So how do we change it? Well, I'm going to be talking a lot about examples today. These are all going to be in Linux just to kind of keep the presentation concise, but a lot of these concepts work equally well in Windows. So here's a Linux command, the sysctl. And what this is going to do is it's going to update the number of the size of my receive window. And then there's actually two commands to do it. One is kind of for all IP protocols across the box, and the other one is specific for TCP. And the TCP one actually has a 3-tuple of values. It's a minimum, default, and a max. And so the really important one there is the max, right? If we don't allow our TCP connection to ramp up past that, then it's placing an artificial ceiling. So if this maximum value is set too low, then you're going to be artificially capping your bandwidth. OK, let's talk about the congestion window. The congestion window has a little bit of a different role than the receive window. Actually, it's very different. The congestion window is hard. It's maintained by the sender. This is where all the magic happens. And I'm going to talk about a lot more detail of this in a few minutes. But let's kind of ramp into this a little bit more gently. So it's controlled by the sender. And what it's trying to do is it's trying to figure out what is the state in the middle of the network. And it's controlled by something called the congestion control algorithm. There's not just one of these algorithms, although there is a default that pretty much all installations of Linux use. It is configurable, and we're going to look at ways to configure it in just a second. And this algorithm actually uses a few different heuristics to try to figure out what the state of the network is. Now, what it's trying to do is figure out if there's congestion on the network, and I send more packets, those packets still might not arrive at my destination. So I'm going to make the situation in the middle of the network worse by sending packets too fast. So I really want to be a good citizen here. I want to send just enough packets to get my maximum throughput, but I don't want to send too many, because that'll make the problem worse for everybody. And so the common inputs you'll see to the congestion control algorithms are loss And this is the dominant one that's used in a lot of algorithms today. So just measuring, if I don't get an acknowledgement back from a packet, right, TCP is based on acknowledgements. I send a packet, I wait for a response. If I don't get the response, either because my sent packet didn't arrive or because the response didn't arrive, which I can't really tell the difference, if I don't get the response back, then I'm going to deduce that there must be congestion on the network. Something's wrong, so I'm going to slow down. Other congestion control algorithms use latency. They'll actually try to time the amount of time it takes from when I send a request and get a response, when I send out that packet and get the acknowledgement back. And then a third mechanism that these algorithms use, especially there's some new ones here, that use bandwidth estimation directly. So they're trying to figure out, probing the link and figuring out just how many packets can I get through, and trying to measure, not indirectly, but fairly directly by using kind of active probing, how much bandwidth do I have on this link, regardless of whether or not there's loss. So I mentioned that the congestion control algorithm has a tough job. And the reason it's a tough job is because it's trying to make this decision about global state from local information, right? It has no idea what's going on in the network. And so when you first establish a TCP connection, the first thing it knows is nothing. It knows absolutely nothing about how far away the endpoint is. It knows nothing about how much congestion there is on the links. And so what it does is it starts slow. And this is what's called the initial congestion window. Now, once upon a time, before 2639 in Linux, the initial congestion window was set to 3. So this 3 is actually 3 packets. And when we're counting a number of bytes from the application's perspective, it's actually 3 kind of maximum segment sizes. So the number of payload bytes will actually fit without all the headers on a packet. So if you get 3 packets, you're going to have about 4,300 bytes of application payload being sent out before TCP waits for its first acknowledgement. Now, this is just a default. And in fact, it was figured out that this actually isn't a very good default. So after 2639, it was actually bumped to 10 in Linux. But we can go even higher if we wanted to. So let's say we wanted to change the amount of initial congestion window for our TCP stack. You can do it with actually on a per route basis. So my convention here on these slides is that the commands I'm going to be typing in, those are in purple. All the output is going to be in black. And if there's something I want you to pay attention in the output, that's colored orange. So I'm going to type IP route change. I'm going to change this one particular route. And the important thing are those last 2 terms, initial congestion window 16. So that means I'm updating the initial congestion window for this route. All new TCP connections that go out this route will have an initial congestion window of 16. And then if I list my routes again, I now see this new value, initial congestion window 16, showing up, even though it didn't before. And if it didn't show up, that basically means it's defaulting to the default inside the kernel. Now, loss is pretty important to many congestion control algorithms. And this is what happens when you get loss on a network. When you have loss and a congestion control algorithm is using that as a signal for how fast to send, it will start backing off immediately. You know, if you ask me a question and say kind of intuitively, 1% of your packets are not reaching the destination. Put another way, 99% of your packets are reaching the destination. How fast do you think your connection would run? Well, I did a little experiment, so this is the graph. The y-axis here is kind of the percent of idealized throughput. So at 0% packet loss, we get 100% of our idealized throughput. But as we start to add just a little bit of loss, at 1%, I'm not at 95, I'm not at 90%. I'm like down less than 50% of my throughput, gone, just from 1% of loss. And the reason is because TCP is backing off very aggressively. It doesn't want to make the situation worse. And it doesn't necessarily know that the loss is because of congestion, but it assumes so. So how do we figure out if there's loss? Oh, I'm sorry. There's one more thing I wanted to mention on this graph. And that is kind of the inverse. If I have an application that has very good network performance, and then suddenly the performance drops precipitously, what could be going on? Well, one potential candidate is that I'm seeing loss, right? If my throughput drops, well, this graph tells me that maybe I'm seeing loss. So how do we figure that out? So the netstat tool is pretty widely known. It's on pretty much every Linux box you'll find in the entire planet. But it's also very coarse-grained. And so what I'm doing here is I'm just grepping out for retransmissions. So what's a retransmission? A retransmission is when a TCP connection sends a packet of data, but never gets an acknowledgement. Now, whatever caused that acknowledgement or packet to be dropped is not going to tell us. We're not going to get some card in the mail that said, by the way, packet number 37, yeah, it's dead. So we have to figure it out. So that we have to, at some point, just give up and say, all right, I'm just going to assume packet 37 never made it. I'm going to send it again. That's what a retransmission is. So here I'm grepping out the retransmission statistics from out of netstat. And netstat is coarse-grained in that all of the connections in the box influence these same counters. So I don't know which particular TCP connection is contributing to the retransmissions. These are also initialized at the kernel boot time. So this particular box has about 58,000 retransmissions, but I don't know if that was from 10 seconds ago or 10 weeks ago. But one of the things that's really helpful when you have a tool like this is to poll it. And not even just poll it, but dump the results of the polling into some kind of metric system where you can graph it. Then you can say, hey, in my graphs, I see a drop in my performance. And hey, in my graphs, I see a sudden surge in retransmissions. Maybe something is going on in the network layer. Let's find out. If you want to go a little bit more fine-grained than netstat, you can use the socket statistic tool, or SS. And the socket statistic tool will give you a huge wall of text about every single connection on your box. So this is one line from SS when I ran it locally. It has a lot of stuff there. I'm not going to talk about every single one of these, but I'm going to walk through a few of them. So the first thing we're going to find here is the TCP state. So this is an established TCP connection. The next thing I'm going to point out here is the send queue. So the send queue is the number of bytes that are pending in the TCP stack to be sent over the network. If this value is 0, that means your application isn't sending any data. Stop looking at the network and go look at your application. So you always want the send queue, if you're expecting good network performance, if you're expecting things to actually be moving, to be greater than 0. Fairly obvious in hindsight. OK, what about this word cubic? It's kind of a funky word. Cubic is actually the name of the congestion control algorithm that's used by this TCP connection. We'll get into that more in a second. We've got a few more here. RTO, that's the retransmission timeout. I said a minute ago that TCP is not going to get a notice that when packets are dropped. So it maintains what's called a retransmission timer that tells it, after this amount of time, just give up on it. Assume it's dead, even if it's not. We also have the congestion control, the initial congestion window. Again, this is in packets, not bytes. So this is scaled up to 138 packets for this particular connection. And then down here, we have the retransmissions for this one particular TCP flow. So again, you can start scraping this output. But it is only going to give you a point in time, right? So you run this command, it just dumps all the output and exits. If you want to go a little bit deeper, there's a great set of tools by Brendan Gregg. Brendan's an engineer at Netflix and has an amazing performance blog, which I really enjoy reading. And he's written some really great tools for inspecting all manner of components in your EC2 instance, one of which is the TCP stack. So this tool, the TCP Retransmission tool, is actually directly measuring retransmissions. The mechanism this tool uses is the kernel ftrace mechanism, which means it's actually instrumenting code inside the kernel. And so when you run this command, it doesn't print out the current state of the connections and exit. It actually sits there and waits for the instrumentation to fire. So every time you see a retransmission, a new line will show up, and a line, and a line. So you can monitor this in real time. If you're like on an outage call, if you're working on an issue live, this tool can be really helpful to figure out, am I recovered? Am I still having problems? What's going on? The other thing nice about it is because it's actually instrumenting the retransmission path in the kernel. It's pay as you go. If you're not sending any retransmissions, then the instrumentation code will never get run, which means you're not paying any kind of performance penalty for the instrumentation kind of in the normal happy case. If you want to find out more about this tool, there's a great GitHub repo there. Definitely check it out. OK, let's talk more about congestion control algorithms. So like I said before, these things are magical. And if you look at the history of congestion control, especially within Linux, it's a little bit of a storied tale. So back before 2.6.8, there was an implementation called New Reno. Then there was a brief experiment with what was called BIC. Then we moved to Cubic at 2.6.19, and that's pretty much where we've been since then. And now we actually have a pluggable architecture. Not now, it's actually been there for quite a while. But there is a pluggable architecture within Linux that allows you to swap these out and play with different ones. And so when I see a history of change in a fundamental component of my kernel, it kind of makes me wonder, why is that the case? Well, one possible answer is it's hard to get right. And so we keep making improvements. We're coming up with new algorithms. There's the active body of research even today into what goes into a good congestion control algorithm. And so we just keep making improvements. That's one answer. The other answer is that the state of the world has changed. You think about back when Linux 2.6.8 came out. Man, that was a while ago. The state of the network was a very different world. And historically, when a lot of the initial TCP congestion control algorithms came out, the world looked very different. So you could think about dial-up. It behaves very differently than broadband, behaves very differently than Wi-Fi, behaves very differently than mobile. But when your congestion control algorithm is running, it has no idea what kinds of networks it's traversing. And a lot of those networks didn't exist back then. So the world has changed. So we iterate and we move forward. Now, there's a bunch of other algorithms out there. I just listed a few of them. BBR, I'm going to talk about in a second. Vegas, Illinois. Illinois is a pretty interesting one. I'm also going to mention that a little bit later. This is not an exhaustive list, but these are ones that you can that are in the kernel tree that you can play around with if you like. So let's say we wanted to do that. The TCP congestion control window, or excuse me, the TCP congestion algorithm is not actually a parameter you'll find on most applications. If you're running the Nginx web server, its config file does not have an entry for what is the congestion control algorithm I should use for this connection. It's possible to set it, but most applications won't expose that knob. And so if we want to play with different congestion control algorithms, what we can do is just change the default for the entire box. So here's a sysctl. The top one there is just listing out what congestion control algorithms are available in my running kernel. Here I have Cubic and Reno. If I want to find out what other ones are currently in my kernel build, I can just use this find command. Chances are, if it starts with TCP underscore something, it's probably a congestion control algorithm. So let's add Illinois. So I'm going to mod probe Illinois. If I do my sysctl again, it now shows up in my list of potential congestion control algorithms. Now again, this doesn't actually change the behavior. It's just now available for use. If I want to change it so that this is the default, I can use this sysctl. And what this means is that all future TCP connections will use the Illinois congestion control algorithm. Now, the bad thing about sysctls, of course, is that you lose them when your box reboots. So if you want to persist it, you can use the second command so that it is the long-term default. And of course, like I said, all new connections. So if you're benchmarking your application and you change this default, be sure to bounce your processes to make sure all open sockets are opened with the new setting. I wanted to give a special call out actually to a newcomer in the congestion control algorithm world, which is BBR. So BBR stands for bottleneck bandwidth and round trip time. This was developed at Google, and they actually run it on a lot of their high-scale applications, including YouTube. BBR has been pushed upstream into Linux 4.9. It's a part of Amazon Linux of 2017-09. So if you got the last two Amazon Linux releases, you can get it. If you're running your own kernels, you can, make sure you're on 4.9. Or you can also grab the drivers are available for older kernels as well. But they're enabled by default. And what's different about BBR is it doesn't actually use loss, at least not directly, to measure the performance or the congestion on a network. It actually tries to measure the bandwidth delay product directly. It tries to measure the round trip time, and it tries to measure the bandwidth. And the way it measures these is it does precise timing about when it sends out packets and when it gets them back. To implement that timing, the initial implementation of BBR actually used a queuing discipline in the Linux kernel. So if you want to play with BBR, and you're on Linux 4.9 or greater, you actually have to run two commands. You have to mod probe this scheduler, this fair queuing scheduler, and then you have to set those to default. You have to turn on FQ as your scheduler, and then you use BBR. The good news is that this second step is actually no longer required as of 4.13, so if you're running bleeding edge or you're willing to wait a little bit, you don't have to do this extra step. And in fact, if you're using a different queuing discipline already, then you can still play around with BBR and not have it take over that setting. OK, so I talked a little bit before about the retransmission timer. This is an important setting to tune, but tune carefully. So the retransmission timer on Linux defaults to 200 milliseconds. Let's say I'm on a network where I have maybe a few milliseconds of round trip time, at least usually. Now, round trip time can be influenced by the routers in the middle, but it can also be influenced by the load of the end hosts as well, the kind of the bandwidth consumed by their network cards. And so all kinds of things can happen even on a low bandwidth network. So if I was to set the retransmission timer to something really low, like 5 milliseconds on a 2 millisecond round trip time, if I get any kind of spurious increase in my latency, what that means is that the retransmission timer will fire, and there might be an acknowledgement on its way back. So I send a packet, I'm waiting 5 milliseconds, it doesn't arrive yet, but it's on its way, and I just assume it's gone, and I send again. And so it can be really dangerous to do this because you can get into kind of a death spiral where your network starts sending more and more traffic that are ultimately duplicates and potentially making what was a spurious event into a long-running event. Now, of course, you wouldn't want to set it too high either. If you set it to 1,000 milliseconds, that means I'm sending, I have 2 milliseconds around time, one packet gets dropped, and I have to wait 1,000 milliseconds until it shows back up. So too high is also bad. So this is a setting that you want to play with care, but it can be an important one to get out some last few decimal points of high percentile latency numbers. So if we want to change it, the RTO is, again, on the routes. Let's say I want to change it on my local network, so my broadcast domain, my AZ subnet, this one right here. And that's a link local address. So unlike the prior commands, which I was using IP route change, to update the link local address, I'm actually going to use IP route, excuse me, I'm going to still use IP route change, but I'm going to use the scope link command, and I'm going to lock it to 50 milliseconds. 50 milliseconds is probably a pretty good lower bound. The reason is something very special happens at 40. So you may have heard of Nagel's algorithm, which tries to coalesce packets on the sender side to make sure that it's not sending fragments of payload. There's something that happens on the receiver side as well, which is delayed acknowledgements. So if I send some packets from Jack to Jill, Jill does not have to immediately respond. She can wait, and if she's going to send some data back to me anyway, she can piggyback her acknowledgement on the data she was going to send. So delayed acknowledgements allows Alice to wait for a little while, and if she's not going to send anything, then she'll just send the acknowledgement. But an acknowledgement is basically pure header. There's no payload, which is why this optimization is there. But the delayed acknowledgement usually comes in at around 40 milliseconds. So if you set this below 40, and you have a system that actually is executing delayed acknowledgements, then again, you can have duplicate packets sent on your packet, which can cause other problems. So what else causes RTO timers to fire? One thing that we found out is it can be caused by queuing along the network path. And so when you send a packet from a sender to a receiver, what happens is that it traverses a set of routers, and each of those routers has an incoming network card that has a buffer. It has a data plane, and the data plane's job is to take packets off the incoming buffer as fastly as it can, do a routely lookup, and then put them on the corresponding output buffer. So you got a pair of buffers there. And what can happen in a high-speed network is you get microbursts on those buffers. Those buffers can back up. You can get a huge queue of packets waiting to get transferred from the incoming buffer, incoming NEC to the outgoing NEC. And what that means is that if you happen to get stuck in a long queue, suddenly you can get a whole bunch of latency that you weren't necessarily expecting, especially if this happened on multiple hops down your network path. So what we can do is try to change the sender to space things out a little bit. If you think about how an application sends data in TCP, it's usually doing a write system call with a huge blob of data down in the kernel, and then the kernel's chunking it up and sending it out in packets. Now, the kernel has the option to send them all out at once, or at least as fast as it can, or it can just spend a little bit of delay in between them, and it still gets approximately the same kind of end-to-end bandwidth, but it helps smooth out some of these interface buffers. So if you want to play with this, there's a command in Linux called TC, which is the traffic control command. TC is one of these Linux commands that is, it is incredibly powerful, but the power is actually rivaled by how difficult it is to figure out how to use. And so if you want to play around with TCP, Google's your friend. You're going to go figure out what other people have done. You're going to find some examples. After you understand some examples, then maybe you're going to go read the man page. And after you read the man page, you're probably going to go read the Linux source code. It's really powerful, but it's a little hard to use. So what I would like to be able to do is use TC. And here's the command I'm going to do, TC QDS list. So what I'm doing here is listing my queuing disciplines. And queuing disciplines are basically a mechanism in the Linux kernel that all outbound packets go through. The initial setting for queuing disciplines in Linux is what's called fast FIFO. So basically, every packet that comes in, as soon as you can, send it out on the network. First in, first out. So we can change the queuing discipline for all packets going outbound. And here, what I'm going to use is what's called the Coddle algorithm, C-O-D-E-L. Coddle actually stands for controlled delay, which is exactly what it's doing. It's just adding a little bit of spacing between all the packets it's sending out to try to help and make sure that we don't get latency spikes from these little microbursts of buffer pileups. If you want to learn more about how Coddle works, there's this website here that has some great information. It's actually a pretty neat algorithm. It doesn't have a lot of tunables, and that's by design. It tries to be pretty smart, in trying to adaptively control how much spacing to put in between packets. And so you can basically just turn it on and turn it off and see the effects. You don't have a lot of knobs to play with. Now, a lot of customers on EC2 are doing things with overlay networks. If your network architecture diagram doesn't have the word overlay in it, and it doesn't have the word VPN tunnel in it, you probably don't ever want to touch your MTU. It's just going to cause pain. But if you are doing fun things like overlay networks, or you're wrapping things up in some kind of a tunnel, like a VPN tunnel, then you want to pay attention to MTUs. Right? MTUs are important because it tracks how many bytes of payload I can put for each byte of header. And I want to include this slide just for completeness, because if you assume that you're just going to default everything to 1500, which is a default in a lot of commands, you're going to be wasting an awful lot of packet processing. And at high speed, the ultimate limiting factor typically isn't the number of bytes in the payload, it's actually packet per second. Because every single packet has to be looked up in some routing table, moved to a queue, and it's the packets per second metric that a lot of times will get in your way. So if you're constrained by packet per second performance, then you want to make sure that you're always using the maximum MTU available. Now, within a VPC, within EC2, you have 9001 jumbo frames, so you can go all the way up to 9001. If you're doing overlays, you're going to have to carve a little bit out of that. Do the math carefully, get it right, and then you'll get a little extra performance. And actually, to make this change, let's say we want to change it here. I'm going to do IP link list. And there it is, MTU 9001. That's my link local address. And let's say I want to change this to maybe 1500. So I'm going to add this I'm going to add this new parameter of 1500 on my route. A lot of these changes are all route-based. So if I list my routes again, I then have a forced MTU of 1500 bytes. Usually you want to go in the other direction, but sometimes you want to bring it down as well. And this is fun to experiment with. OK. No talk about network performance would be complete without talking about enhanced networking. So enhanced networking was released a few years ago, 2014. And what it allows EC2 instances to do is get more bang for their buck in terms of sending out packets. Now, the way this works, and Peter DeSantis talked about this a little bit the other night and hinted at it, is when you're sending data out of a TCP connection, it doesn't actually take that kind of idealized back and forth I talked about. It actually goes through a few different hops, especially when you're on a cloud-based virtualization technology like Amazon EC2. So what's exposed to your guest operating system is actually what's called a Xen paravirtualized driver. So every packet you send out goes through this Xen PV driver. It then passes through the virtualization layer, which then sends it on down to the NIC and off onto the wire. Now, these extra hops that your packets are taking are adding latency, but almost more problematically, they're adding jitter. Some packets might be fast, some packets might be slow. The virtualization layer might be busy doing something else at that exact moment. So you're not actually, when you think you're talking to your ETH0, you're not actually talking to the hardware. You're talking about to this hardware abstraction layer, which is adding latency to you. So what enhanced networking did is we said, you know what, we're going to skip the virtualization layer. We're going to go directly to the NIC. And the first version of enhanced networking used Intel NICs. It was 82599s. And these allowed 10 gigabit throughput. And much more importantly, much less jitter. So if you look at the metrics that we posted back when we first launched this, it really are impressive. Now, the Intel NIC is a pretty neat card, but unfortunately, it's a 10 gig card. And as we've started to move to the Nitro system and move a lot of our networking components off onto our own hardware, we knew that we were going to have a roadmap where this bandwidth of this device was going to start to increase. So last year, we introduced the Elastic Network Adapter. And the Elastic Network Adapter conceptually is very similar to the Intel card. It's a box that exposes virtual functions up to the guests. You know, the academic term for this is SRIOV, single root IO virtualization. And these virtual functions are what the guest operating use to talk directly to the NENA driver. Now, when we first launched NENA, we actually allowed 20 gigabit streams. And then a few months ago, we actually bumped that number to 25. And the great thing about that bump is you didn't have to do anything. The 25 gigabit came for free. You get 5 extra gigabits, no extra charge, no hidden fees. So how do you know you're using NENA? Well, you can use the ETH tool to find out what driver your kernel is using. If it says VIF, that means you're using the Xen PV driver. That's fine. The ZenPV driver works great. It's going to be the only thing you have on older instance types. If you're on enhanced networking, there's the Intel driver here. And then on ENA, the driver is just called ENA. And that was, in fact, by design. On our roadmap, we're going to be continuing to ramp up the bandwidth that is going to be available on these cards. So today it's 25, in the future it might be 50, 100, and so on and so forth. And every time we did that, we didn't want to make you guys have to change what driver your kernel was using. So when we built this ENA driver, this driver is meant to go up to 400 gigabits, no changes. All new future hardware will just take advantage of that as we go. As the hardware has evolved over time, I've tried to get a list of the different instance types. We just launched C5 a week ago, so C5 would be on the ENA list as well. Basically, all new EC2 instances going forward are going to be ENA enabled. If you want to get the drivers for the ENA device, you can download it from their website. We've actually pushed them upstream into Linux 4.9. So if you're running the latest Amazon Linux AMI, if you're running the latest kernel from other distributions, you should be able to get it for free. If you want to do more exotic things, if you're running DPDK, there's also DPDK drivers at that address, as well as FreeBSD drivers. OK. Lots of talk. Let's play with some toys. So I want to go through a few examples. Again, these are toys. They're made up. But let's see what changes we can enact. And the changes I'm going to be making here are just to the Linux stack. I'm not going to touch the application in any way. I don't assume that I'm going to have the source code. I don't assume I'll even necessarily know what decisions it's making. But assuming a fixed kind of application, what can I do just with the network stack? So here's my test setup. I've got a pair of M4 16XLs. These are my Jack and Jill. I'm going to be running a recent Linux kernel. I'm using the Amazon Linux from, I think, a point release ago when I first made these. Using Nginx. My client is going to be Apache Bench. Apache Bench is a little bit older. It's not the best of breed necessarily if you're looking to benchmark a brand new web server, but it's pretty predictable and I know it pretty well, so I'm going to use it as my kind of client in these examples. I'm using SSL for all these connections. Those are the parameters I'm using in case you want to play along at home. All the data I generated were just catting dev random. They're served out of a tempfs directory, so there's no I/O whatsoever. The client throws away the bits. So really what I'm trying to do in these experiments is focus exclusively on the network, throwing out all the other parameters of variability and just see what can I change about the network. So the first application I'm going to go through is this loss situation. So I gave that really funky graph earlier when we just get a little bit of loss and throughput really drops off. So if you're in a situation where you have loss, maybe you have a lot of customers that are mobile users, and loss is just going to be part of the day, part of your life. Maybe you just can't get around it. Or you want to make sure that just in case loss happens, your application is minimally impacted. What can we do? So here's my setup I'm going to use. I've got a pair of instances. They're 80 milliseconds apart round trip time. I'm going to be running this Apache Bench command. And then I'm going to use this TC tool, which is quite the Swiss Army knife, to add 0.5% of loss. The TC tool has a lot of parameters. You can actually change like the probability distribution of this loss and make it much more realistic. This is going to be uniform distribution. It's probably not terribly realistic, but it's fun for a demo. OK, so our goal here, given 0.5% loss, how fast can we go? Now, what I did in this experiment was I was running Nginx, and I just dumped the output of Nginx into CloudWatch. And I realized that these graphs, you probably can't read the x or y-axis. The x-axis is time. The y-axis is the milliseconds for a request. And the two lines here are the P50 and P99 for those requests. So what are P50 and P99? They're fancy words for percentiles. So when a lot of times when people talk about performance numbers, they use average. Don't use average. Use median. Median means 50% of your customers are getting this percent of this performance or better. P99 means this is the 99th percentile. 99% of your customers are getting this or better. Sometimes you have no choice to use average, but if you can, you should always be looking at percentiles. It gives you a more complete picture of what's going on. OK, so in this experiment, baseline, I haven't added my loss yet. This is just kind of getting things started. My P99, 99% of all my requests ended in 37 seconds or less. 50% of them were 23 seconds or less. Let's add our loss. OK, everything got slower. My P99 is now 52 seconds. My P50 is now 42 seconds. So what can we do? Well, I was talking about congestion control algorithms earlier and saying that a lot of them use loss as their primary indicator of congestion. So why don't we start playing with some congestion control algorithms? So the first thing I'm going to play with is, so I'm going to put cubic here on my left. That's the graph we just had, just changing the title a little bit. And what I'm going to do is I'm going to look at Illinois. So Illinois is a congestion control algorithm that does not have quite the sensitivity to loss that cubic does. So I use Illinois, boom, right away. My P50 has dropped almost in half, and my P99 has come down as well. Let's see, what else could we do? What about BBR? That was supposed to do something interesting. Even better. My P50 is now at 11 seconds. So just from changing the congestion control algorithm in this experiment, changing nothing else, I've gotten a 74% decrease in my P50 latency for these requests. Now, you might be wondering, or if you're still awake, you think 11 seconds, isn't that lower than what I had without any loss with cubic? And yes, you'd be correct. In fact, BBR performs better with loss than cubic did without loss. Is that true in every situation? Probably not. It's an artifact of these particular experiments. But I get to compare them side by side and see what am I trading off here. And in fact, if I remove loss from BBR, it gets even better, right? BBR's best case scenario here is now 8 seconds at P50 and 44 seconds at P99. So is this a talk to tell you that you should go play with BBR? Yes. Is it going to solve all your problems? No. And is this going to represent what you're going to see in your applications? No. Let me show you one more paragraph. So this paragraph shows you the cubic no loss versus the BBR no loss. So as we can see, the P50 on the BBR is much, much better. But the P99 is actually more spiky. Is my application really sensitive to jitter? Maybe BBR isn't the right solution for this particular benchmark. Now again, this might also be artifacts of this particular experiment. So this is what I want you guys to take away from this presentation. Not that go use BBR, but start looking at what happens when I change these. What happens at different percentiles? Don't assume one number is going to summarize everything about a performance benchmark. OK, so that was an 80 millisecond link. Let's talk a little bit about a low RTT path. What about, let's say, 2 milliseconds? Or sorry, 1 millisecond. And for this one, I'm going to be transferring a pretty small object, just 10 megs, but over and over and over and over and over and over again. And what I want to look at here is actually the retransmission timer when I add a little bit of loss. So these instances are closer together. I'm only going to use 0.2% in this experiment. The last one was 0.5. Same TC command. I didn't put it up on the slide, but you can extrapolate from the prior one just at 0.2 instead of 0.5. So if I'm running this experiment and I graph my data without any loss, my P50 is about 2 excuse me, with loss. This is with loss. So if I graph my latency with loss, 0.2% loss, my P50 is at 2 milliseconds. Pretty fast. 10 meg file, 2 milliseconds. Yeah, that's pretty fast. What about a really high percentile? P99.99. 200 milliseconds. That's 2 orders of magnitude higher than my P50. Now, these y-axes are not to scale. I had to use different scales because if I put them on the same y-axis, you couldn't even see the 2 milliseconds. It'd be down on the floor. So why do we care about such high percentiles like P99.99? Well, that means 1 out of every 10,000 of your customers are going to experience this. But it's actually probably worse than that. If you think about what happens today in a lot of our architectures, they tend to be service-oriented architectures. We like microservices. We like to break things apart. So if you think about the P9999, you have to think about all the hops it goes through to actually satisfy one customer request. Could be dozens of microservices. And when you start adding up dozens and dozens and dozens of P9999s, the probabilities start to collapse, right? So now it might be 1 in 100 customers are experiencing this, or maybe 1 in 1,000. And you really want that customer to have a good day. So what can we do about this 200 milliseconds? Well, what do we know about 200 milliseconds? It's the default RTO for Linux. Let's try dropping it. So instead of 200 milliseconds for the default RTO, let's drop it to 50. And just making that one change on the IP route gets me half of the latency back at this high percentile. Now, why is it not P50? Well, there's probably other things going on. At a really high percentile like P9999, a lot of things, just like a few packets here and there, have to have a bad day to cause this to go wrong. But what I found here is that half of the problem was just the RTO. By dropping the RTO min, my really high percentile performance gets better. And in fact, twice as good, which is pretty great for a one-line change. OK, third application. This one is going to be a high transaction service. Now, this one, I'm actually going to use HTTP. The previous examples were all HTTPS with SSL. And the reason is I'm going to be going down to looking at individual packets and what's going on there. So I'm going to do, my instances are a little bit farther apart this time. I'm going to assume there's a 1,500 byte MTU. And I'm going to make 200,000 requests for a little tiny 10K object. So what do we expect to be 10K? Not many things these days, right? Well, there's a few things. Web pages, HTML files, thumbnails. A lot of web requests fall into this category of short-lived connections that transfer a relatively small amount of data. Now, hopefully, it's for using that connection in the future, but not always. If you have a web page which is relatively static, relatively small, you might get one TCP connection and you're done. Similarly with API requests. Your API request might only be transferring a little bit of data. 10K is not unreasonable for an API request, right, if you have a web service. So let's look at what happens with a congestion control, and specifically the initial congestion control window, what happens on these two servers that are 80 milliseconds apart. So when I run this test, I'm going to start out at 3 packets. Now, as I mentioned before, most modern Linux distributions don't have this setting this low, but I'm going to start here. We do have customers that run old kernels, so it is something to look out for if you are before 2.639. But at 3 packets for my initial congestion window, it takes 321 milliseconds to transfer a 10K file. What in the world is going on? So 321, or how about just 320, is an awfully suspicious multiplier of 80. Right? It's about 4 times 80. And so what's really going on here is to transfer that 10K file, we had to do 4 round trips, 4 times. So let's try playing with this. What happens if we go up to 10 packets as our initial congestion window? So what this means is I'm now sending 10 packets and before waiting for my first acknowledgement. So I get all those out. And what I've done by doing that is eliminated an entire round trip from this request response. So now my latency has dropped at P50 to 241. Let's keep going. Let's go to 16 packets. Now I'm down 161 milliseconds for my P50. And as I'm doing this, the actual effective bandwidth on my NIC is going up dramatically, right? I'm getting a lot more utilization. If I'm concerned about optimizing my costs and how many requests I can handle on an individual box, this is starting to make a difference. And so at a congestion window of 16 packets, an initial congestion window of 16 packets, I'm down to 2 round trip times. And that's probably about as good as you're going to get for an initial brand new TCP connection. Because you need 1 for our handshake, of course, and then 1 to actually transfer the data. And of course, the bandwidth has now increased by 79%. OK, what do I hope you take away from this talk? One is that the network doesn't have to be a black box. It can be pretty easy to blame a lot of problems on the network. Oh, network problem. Transient, resolved. Don't do that. Take a look, use the tools, figure out, was it a networking problem? And where might it be? Just because you're seeing packet loss does not necessarily mean that the middle of the network caused it. You can try to track that down. If you have middle boxes, you want to try to figure out where you're introducing retransmissions, where you're losing packets. And you want to figure out, if I see sudden shifts in behavior in my application, is it even possible that it's networking, that it's packet loss? If you're not seeing any retransmissions, chances are there's not any packet loss. Keep digging, find the true root cause. The second takeaway is these tweaks are pretty simple. And hopefully, I'm going to enable you to go from here and start playing. This isn't going to take hours and hours. You know, I did these experiments fairly quickly, and they're a lot of fun to play around with. Now, of course, with any kind of performance tuning, you want to be very deliberate. Change one parameter at a time. As close as you can, test your production use case. If you can replicate, if you have a production VPC, can you create a test VPC that looks the same where you can start playing around with these? Try to use your exact data. because a lot of performance troubleshooting is going to be very, very specific to the details that you're seeing in a production stack. And then finally, understand what your application needs from the network. If it turns out that the send queue that the socket statistics tool is telling me is 0, does that mean the network is a problem? No. Maybe my network has some global mutex, and it's butting against itself. Is it really blocked on the network? Maybe it's spending most of its time reading bytes from disk and then sending the network. And if you're not measuring those individually, if you're measuring them together, then you might say, oh, it's a network problem, but it might not be. So make sure when you're benchmarking, when you're benchmarking, that as much as you can, isolate the networking effects to make sure that you can effectively kind of triangulate where these problems are. So thank you very much for coming. I'm going to be up here in the front afterwards if you have a few questions. Please remember to fulfill your evaluations at the end. There we go.